The research paper presents a symmetry result regarding stationary solutions of the 2D Euler equations in a disk. Specifically, it proves that in a disk, a steady flow with only one stagnation point and tangential boundary conditions is a circular flow, confirming a conjecture proposed by Hamel and N. Nadirashvili. The Euler equations, a set of nonlinear partial differential equations, describe the motion of an ideal fluid in a planar domain. The authors focus on the geometry of the domain and its effects on the properties of steady flows, seeking conditions that ensure solutions inherit the geometric symmetry properties of the domain. The conjecture, proposed by Hamel and Nadirashvili, states that if a flow has only one stagnation point in a disk and satisfies the tangential boundary condition, then the stagnation point must be the origin, and the flow is circular. The authors provide a positive answer to this conjecture, proving a slightly stronger result that requires the flow to have a single stagnation point within the domain. The proof involves transforming the problem into the symmetry of solutions of a semilinear elliptic boundary value problem in the disk. The authors use a stream function, which is a scalar function that satisfies the Euler equations, to reduce the problem to a semilinear elliptic equation. They then apply a rearrangement technique called continuous Steiner symmetrization to establish local symmetry properties for non-negative solutions of the semilinear elliptic equation. The main result, theorem 1.3, states that if a flow has a single stagnation point in a disk and satisfies the tangential boundary condition, then the stagnation point is the origin, and the flow is circular. The proof involves showing that the stream function is radially decreasing with respect to the origin, which implies that the flow is circular. The author's approach builds upon previous results in the field, including a famous result by Hamel and Nadirashvili that shows that in a strip, a steady flow with no stationary point and tangential boundary conditions is a shear flow. The paper contributes to the understanding of how the geometry of the domain affects the properties of steady flows, providing insights into the symmetry properties of solutions of the Euler equations in a disk. In the context of fluid dynamics, this research paper focuses on the Euler equations in a disk, aiming to establish a Liouville theorem for Beltrami flows. The authors first present an auxiliary result, proposition 3.1, which states that the corresponding stream function of a steady flow satisfies a semilinear elliptic equation under certain assumptions. This proposition is crucial for the proof of the Liouville theorem, as it allows the authors to deduce that the stream function is constant along any streamline of the flow and that the vorticity is uniformly continuous in the disk. The second auxiliary result, proposition 3.2, is about the symmetry of solutions to semilinear elliptic equations with a continuous nonlinearity in a ball. This result, adapted from 2, provides insight into the structure of solutions, revealing that they are locally symmetric, radially symmetric, and radially decreasing in annuli, and flat elsewhere in the ball. It also highlights the properties of the sets AC, which are pairwise disjoint and may be finite or infinite in number. The authors then acknowledge the helpful discussions with Professor François Hamel and cite relevant references for further reading. These include papers on continuous Steiner symmetrization, 1, symmetry and stability of non-negative solutions to degenerate elliptic equations in a ball, 3, and remarks on a Liouville-type theorem for Beltrami flows, 4. The research discusses a Liouville theorem for the Euler equations in a disk, focusing on the fluid dynamics and its mathematical implications. It draws from various studies, including those by Constantin et al. And Hamel and Nadirashvili, which explore steady fluid motion, symmetry, and the properties of Euler equations. The authors examine the flexibility and rigidity in steady fluid motion, as well as the existence of symmetry-breaking solutions. They also investigate the Euler equations in unbounded domains and in two-dimensional annular domains, highlighting the importance of circular and parallel flows. The Liouville theorem, a fundamental concept in the study of partial differential equations, is applied to the Euler equations to establish the existence of solutions with specific properties. The research emphasizes the significance of these findings in understanding the behavior of fluids and their applications in various fields.